Good morning, developers. If you are new to the channel, my name is Rob, and it is CS Thursday, the day that we focus on the theory behind our craft, how stuff works. And today that leads us to Big O notation. There's almost always more than one solution to a given problem. If you and a coworker work on the same ticket or a code challenge independently of each other, you may come out with different implementations, maybe even radically different. Which one is better? And if one's better, how would you even know? Well, that is what Big O notation is after. And you maybe are thinking immediately, Rob, if I come to the right solution or if my code works and so does theirs, what difference does it make whose is better? That's just an elitist approach to code. Well, it can make a huge difference if the data set starts to get big. And that's what Big O notation wants to answer. So let me give you for instance. Let's say you have a bookshelf in your office, right? Not many people have hard copy books anymore. So you've got 6 books. It doesn't make any difference if you have an organizational system. They could be upside down, sideways, they could be stacked on top of each other. You'll be able to find the one you want almost instantly every time. Having them organized, having them alphabetized, it might make a tiny difference, but it's not really going to be a big deal. What if you went to the public library and they had no system? People could just walk in and drop a book on the floor, they could put it on the table, on any shelf, upside down, backwards, whatever. That would be a disaster because they have like 100,000 books. Or the Library of Congress in Washington, D.C. has almost 15 million books. No one would use the library. It would be a complete disaster. There would be books everywhere. You'd never find anything. That would not be okay. That's where we are going with Big O notation, is trying to determine how efficient a given algorithm is when we get to those Library of Congress type levels. And maybe you're thinking, Rob, I work at a small company, a small data sets, right? We don't get a lot of traffic, etc. This doesn't matter. In my experience, it does matter to you as a developer. And I care about that as an instructor, as a teacher. I have a Project Euler playlist, and I'll drop it in the description. But as I have gone through those, it very much is working on optimizing, because a lot of times the brute force solution won't work. It has made a huge difference just in the way that I code. It does matter in the long run as a developer because you'll be more creative, you'll see more than you had in the past. You also never know when your code is going to boom, when it really takes off and it's going to be needed to perform well. It's not a very positive example, but I thought it was really funny. I met the web team for a really popular video game. If you're into video games, you definitely would have heard of it. And they were rolling in a new website, and they had planned for traffic on a bad day and then added a bunch of margins so they were ready. What they didn't account for was the fact that this is a video game, and if the servers go down in South Korea or the Eastern United States or whatever, suddenly 5 million people hit the website because they can't go to the game anymore, and they start posting like crazy. The website crashed almost instantly, right? That's a crazy example, but all of a sudden you go from just normal traffic to boom, huge traffic, and that's when it does matter. So you never know when that's going to happen. Typically, when we look at the Big O of a given algorithm, we're talking about the worst case scenario. So like in the case of the web developers, the best case scenario, that would be like if you go to a library, they have no system, you don't check, you just walk up, grab a copy of a book, and it happens to be the one you're looking for, right? Great, but that usually doesn't happen. Average case would be if you ran this multiple times, what's usually the length of time or the number of operations. Worst case we do because it makes sure that it's predictable. Even on our worst day, if we get hit with malicious code or some crazy viral situation or an insane data set we weren't counting on, we will still perform this good. Predictability is always good as a developer. And so the chart that you will see all over the internet is an X and a Y axis. And the X axis is going to be the number of inputs. So we'll typically use arrays or lists because those grow. Those are very easy to demonstrate. They grow. Along the y-axis, we will have the number of operations. You will see that, and you will also see time. Those two things are typically correlated. As the data set you're working on gets bigger, the number of operations will get bigger, and so will the time increase as well. Okay? We're going to increase from the most efficient or the most ideal to the least, and that means we're going to start with an O of 1. That means that it doesn't make any difference how big the data you're working with is. It's gonna take the same amount of time. So as for instance, a contrived example you'll see all over is we have a function called sum that brings in an array, and this thing simply returns, array 0 plus array 1 or whatever, right? Doesn't matter if there's a billion elements in that array or there's only one element, this is going to take the same amount of time. The same thing would be true if in this same function, maybe we have a loop and we're going to do for I from 1 to 20. Again, it doesn't matter that we're going to run 20 times. It just matters that it doesn't matter how many elements there are. It's always going to take the same amount of time, and that's something to remember here. We're comparing algorithm to algorithm. We're not comparing how this algorithm runs on a given machine, right? Because a given piece of code that runs on a supercomputer will run really fast. Same code on a 1990s flip phone, really slow. We're talking about, right, these number of steps. As the data gets bigger, it won't make any difference in how long it takes to run. Let me clean this up quick. Our next one is not going to be quite drawn to scale, but this is going to be a log n. And so big O of log n. This increases with a very subtle curve. So as we get more and more inputs, it gets bigger, slower, and slower. And the way to think about this one is if we had the numbers 1 through 8, actually I'm going to go out to 9. If you were looking for a number in this sorted list, you could start at the middle number. Is it bigger or smaller? And if it's smaller, you only have to deal with half the list. So from here, you do the same thing. You'd end up with half the list. From here, you'd end up with half the list. So a list of 9 elements can never take more than four tries because you split it in half every time. The good thing here is that log n means in order to go up just one number, right, one unit of time or one operation, you have to double the number of elements that you've got. So this is going to be the same all the way out to 15, not until 16, because that's a factor of 2, and that's when you're dividing, you're splitting them in half. You have to increase out to 16 before you need even one more operation. The next one is if we increase at a linear rate, that is going to be a big O of n. And that just means that as n gets bigger, the amount of time gets proportionately bigger as well. The easiest way to think about this one is just a loop. So for I from 1 to 20, if I goes from 20 to 200, you have to loop 200 times, 2,000, 2,000 times, and so on, right? As n gets bigger, we have to do more work. They move proportionately to each other. This is probably the most common one in programming because we have to loop over lists and arrays and things all the time. The next one is n log n, and I'm not going to be able to do it justice here because the curve is probably too severe, but it's the same as log n down here, but we are multiplying n times it. So again, a big O of n log n. This is going to be the king for the best sorting algorithms. Typically, that's what they are. So if you have a list that's not in order, you have to loop over everything. So we'll have for I from 1 to n, right? So this is the n part. We have to loop over every element. But inside here, we're able to take this and we're able to split it in half each time. That's the log n part. So merge sort and heap sort, they are n log n. This is again about as good as you're ever going to be able to do on an unsorted list. The next one is where things start getting ugly, and this one is still quite common. This is n squared. And n squared is probably what you saw coming with O n. That was a simple loop. N squared, we have 4i from 1 out to n. Inside there, we have to loop over everything again. So for j from 1 to n. An example of this would be bubble sort. We loop through every slot, and then we have to loop through each number for each slot. So if this happens to be a list of 10 things, 10 on the outside times 10 on the inside means we have 100. That's why this is parabolic, or quadratically. This was made by a German mathematician, so we have some algebra lingo in here. But just 10 in, we're already at 100. If this was 100 elements, 100 times 100 is 10,000. So it goes up very quickly. This is not great, but sometimes you do have to loop twice. It's just we always want to be moving our way up. Another one that I'm not going to put up here because it's pretty self-explanatory and it's not all that common. I'm going to put n to the ith power. Every time you nest a loop, so if you have 3 nested loops, that's going to be n to the third. It will just create a sharper parabola. So the next one is going to be 2 to the nth. And I hope you never end up in this situation because this is really bad. It is the exact opposite of log n. It means every time you add one element, you double the number of operations or you double the amount of time that it takes. And so, as a for instance, 2 to the 32nd power, that's just over 4 trillion. If you have a log n, that means in 32 operations, you could deal with a list of 4 trillion. Just the opposite, it means if you have 32 elements, it's going to take 4 trillion operations. That's bad, right? We want to avoid this. It would be common like in a completely exhaustive recursive solution. So like the Fibonacci sequence, if you recursively solved every single number, every time you add one number, you double the number of operations or the amount of time that it takes to finish. And the last one we're going to look at looks pretty much like that, and this is n factorial. Hopefully you never do this one. Usually you kind of have to try. This would be some completely exhaustive permutation. BOGO sort, you can search for it if you want to. It would be you have an array and you want to see if it's sorted. You just randomly put all the elements in a spot and check to see if it's sorted. If it's not, you do it again. Just randomly put them in order. It's going to look like this, where 2 has a value of 2. 3 is 3 times 2, which is 6. 4 is 4 times 6, which is 24. 5 is 5 times 24, which is 96. We're only 5 in and we're almost at 100 already. So this gets miserably bad really fast. These are the most common big O notations when it comes to time, or again, the number of operations. There is also space, and there's not a ton to say here. Typically, when it comes to sorting algorithms, which is where I spend my most time, a big O of 1 will mean that the algorithm is sorting in place. So like bubble sort, you're not going to make a copy of the array. You're just going to loop over it, and you're going to switch elements. It doesn't require any extra space, any extra memory, or whatever you might be using. Something like merge sort has a big O of n when it comes to space because you make an entire copy of the array each time through, so that will take up more memory. And if that's a concern, then you have to start looking around. Okay, I'm taking up too much space. I need to find a different algorithm that sorts in place, or whatever the case might be. Okay, thank you so much for watching. This is absolutely worth continuing to unpack, looking at algorithms that do each one of these, because this is a fairly complete list. But it's really interesting to how do you get from n squared to n log n, or how do you get from n to log n, or something like that when you're coding. That is the really fun part and interesting, not just because it will save money, it will save end user time, it will save all over the place. It will make you a better developer. And that's primarily what I'm interested in, is finding better solutions, being more creative, making yourself more useful, working your way down, or in this case, up. Thanks so much for watching. I will see you next time on CS Thursday.